Thank you for attending this presentation. My name is Zhending Zhao from Taiwan National Tsinghua University. This paper is advised by Professor Cont. I'm going to present Devise Sparse compression schedulers to enhance FastText method. And this project is cooperating with Xiangwei Song and Mingyu Hong in MediaTek, which is one of the IC design house leader in Taiwan. My presentation is divided into 4 main sections. First, I will introduce the background of this study. Second, it will be the scheduling primitive in Halide, and this is the method with which we implement our work. Then, we show an application example, which is FastText, a machine learning library from Facebook. And finally, we conclude this paper in the end. Sparse matrix is a matrix which contains few non-zero elements, and it usually appears in neural networks after zero padding or pruning. For example, convolution is a layer to extract features from input images. It's a mathematical operation that takes image matrix and a filter over kernel as inputs. As we can see in example A, the output is actually not the same size as the original input, and we may lose variable information around the edge of the inputs after convolution. However, as shown in example B, we can use zero padding to add zeros around the outside of the input image and overcome the above problem. And this will make input array become sparse. Weight pruning is a set of methods to increase the sparsity of weights and reduce the storage and the computation of neural networks. The most common pruning criteria is the absolute value of each element. Compare the element's absolute value to the threshold, and if it's below the threshold, the element will be set to 0. The above process will convert a dense network into a sparse network, as illustrated in figure. This slide illustrates how to perform COO, CSR, and ELO compression format. In COO and CSR format, the matrix is compressed into 3 one-dimensional arrays. And we can see that both formats stores the color index and element values. The difference is that COO stores the row index, but CSR stores the row pointer. Compared with COO format, CSR format can access the rows more quickly, while in contrast, in the ELO format, matrices are compressed into two-dimensional arrays, which are used to record the color index of non-zero elements and their value. Halide is an embedded domain-specific language, which is originally designed for high-performance image and array processing. Here it shows a simple Halide program. In this program, we can see that the algorithm is decoupled from scheduling. The benefits of Halide is that it takes care of the implementation details of optimizations, so programmers can focus on the algorithm design, while less convenient with the many scheduling strategies provided by Halide. We hope its scheduling primitive can support sparse matrix compression, which is currently unavailable. This Halide program describes how to do a simple multiplication. In this work, we implement 2 new scheduling primitives in Halide, namely the COO and CSR sparse matrix compression schemes, and use them for matrix compression and computation. This is a small part of our implementation. Internally, a Halide program is represented as an arbitrary syntax tree of Halide IR nodes, and we traverse this tree to obtain data and analyze the described algorithm. However, we find that each format has its pros and cons. For example, the EL format can give better performance than the CSR format with structured matrices. So we hope to develop a more general and computationally faster format. We take advantage of EL and the CSR format, which provide performance and flexibility to propose a hybrid compression method. The following slides show the algorithm of our hybrid compression method. Then we will use a simple example to demonstrate the algorithm. Algorithm 1 shows the algorithm for our hybrid compression method. Let m column and m value denote two arrays that stores the column index and the value of non-zero elements, respectively, as shown in third line to 13th line. The algorithm traverses the entire source matrix and finds out non-zero elements for each row. If a non-zero element is found, its column index and the value will append to the corresponding row of m column and m value. After this process, we can obtain tensor matrix in the EL format. During the compression, we denote threshold as the number of non-zero elements divided by the row size of closed matrix. Depending on the threshold, the algorithm divides a matrix into two submatrices. One is denser and another is sparser. This slide illustrates the overview of our reorder algorithm. If a row in the original sparse matrix has fewer non-zero elements, the corresponding row in the EL format will be zero-pended until its length is the same as the length of other rows. As shown in left picture in this slide, the white space in the dense block represents the zeros filled by padding. So we redistribute the data position, move the elements from sparse block to replace zeros, and reduce overall computing costs. In the process, since the position of the selected elements have been changed, a record table will be updated to fix the final calculation result. In this final step, we compress the sparse block in CSR format. The above is the process of our proposed method. In the third part, we describe how to extend FastText to improve its performance. Let's begin with FastText. FastText is an open-source library developed by Facebook's AI Research Lab for efficient learning word embedding and text classification. It provides two models, skipgram and Siebel, for calculating word embedding. Word embedding is a technique widely used in natural language processing, which uses vectors to represent each word. After training, we can get a matrix in which each row represents one word. However, the matrix is dense without lots of zero elements, so we must do some processing on the matrix before using our method to optimize FastText. As you can see, after pruning, the matrix becomes sparser than before, and there is not much difference in calculation results. The next two slides describe how we optimize FastText with our method. After taking word datasets to train models in FastText, we can get pre-trained models and in the original FastText flow, which is as shown in this feature. They will be directly used to do NLP application. However, in our flow, after loading the pre-trained model, we will prune the weights whose values are below the threshold, and then the pre-trained models will be optimized by our method. The above optimization process can be done offline, so the pre-trained models only need to perform our method once without bringing too much overhead to the runtime. Halide supports JIT and AOT compilation. In our work, we adopt AOT compilation, which is to compile the code before execution, and separate the execution time from the compilation time. We write array processing code in Halide, and use Halide code generator to generate the target code. The Halide compiler will produce an optimized binary. And finally, we load the optimized model and the optimized binary into FastText to do NLP application. In the experiment, we take the Wikipedia dataset to train the two models of FastText, namely skipgram and Seaball, and get the pre-trained models. Then we adjust several thresholds to prune the models and optimize it with our hybrid compression method. Semantic similarity plays an important role for NLP application. And in mathematics, we can measure similarity between two vectors by using cosine similarity. In the rating stage, we randomly choose 10,000 different words from the IMDb dataset and use them to query for word similarity. If the top result of the modified FastText is not within the top 5 results of the original version, it will regard as a wrong answer. This table shows the environment configurations used in our experiment evaluation. What's here is our experimental results. We focus on the relationship between sparsity, speed up, and the error rate. Due to our proposed method, which compress models, our evaluation result shows that we can speed up FastText by 1.2 to 1.9 times compared to the unmodified version. Finally, let me conclude this paper. We propose a hybrid compression method that combines CSR and ELO format, and we design a reorder algorithm to support this method. The COO CSR metric compression schemes and the proposed method to combine them are implemented in Halide to support sparse metric optimization. In addition to this, we conduct an experiment with a modified version of FastText, which processes the pre-trained model with our method, and use the Halide code generator to produce optimized binary. The evaluation result shows that the proposed method optimized FastText with a 1.2 to 1.9 times speed up gain compared with the original one. Our method can greatly reduce computation workload of an applicable model with limited accuracy loss. This is the end of my speech. Thank you for your kind attention.